Aircraft used in Army aviation today are far more complex than they were only a few years ago. Many of the new controls and accessories are electrically operated. Electrical trim, fuel pumps, windshield wipers and heaters, warning lights, fire detectors, loading lights, chip detectors, communication and navigation equipment. All of these instruments, warning devices and flight aids may be electrically operated, and all of them can develop electrical trouble. The failure of some of these critically important electrical devices could ground the aircraft. The return of an aircraft to its assigned mission depends primarily on one thing: the skill and knowledge of the responsible mechanic. Aircraft circuits have become complicated as well as numerous. The mechanic must have a thorough understanding of the many types of wiring diagrams, isometric drawings, and equipment lists found in the aircraft -20s. He must be able to read and follow the wire identification codes, and he must understand the common diagram symbols. Wiring diagrams are absolutely necessary on any electrical repair job. No one, not even the most experienced mechanic, has every detail of every circuit in his head. A wiring diagram is the most valuable tool you can have on any electrical troubleshooting job. Troubleshooting. Electrical troubleshooting. That's our subject. Exactly what does it mean? Electrical troubleshooting is simply a technique for systematically locating faults in an electrical circuit. That's what we're going to learn right now: the tools and techniques for systematic troubleshooting. 3 items of test equipment are used. One item is an electrical measuring device called a multimeter. The other 2 are a jumper wire and a continuity test light. These 2 simple devices are all you will need for many troubleshooting jobs. They should, however, only be used by experienced personnel. Later, we will see how you can make them yourself. A multimeter can do everything a jumper wire and test light can, as well as providing the extra sensitivity required for some electronic and instrument circuit testing. A multimeter looks quite complicated, but it is not difficult to learn to use one. Multi means many, and a multimeter is actually many meters in one. The multimeter which you will be using contains an ammeter, a voltmeter, and an ohm meter. Ammeters are not used in electrical troubleshooting, so we will not deal with them at this time. Voltmeters and ohm meters are very useful, and you must know how to set up the multimeter for either of these 2 functions. First, see how the multimeter is set up for use as a voltmeter. You start by adjusting the function selector switch. This switch, as its name implies, is used to connect the proper internal circuits for each of the multimeter's functions. The proper selector switch setting for voltmeter use is direct. With the function selector on direct, the only other thing we must know is where the red and the black test leads are plugged in. Just above the scale on the left side is a jack marked -DC, plus or minus AC. For voltmeter, as well as ohm meter applications, you will always plug the black test lead into this jack. Beneath this connection, there is a row of 6 jacks. The red test lead will go into one of these jacks. Note that the jacks are labeled 2.5 volts, 10 volts, 50 volts, 250 volts, 500 volts, and 1000 volts. If you do not know the voltage of the circuit you're testing, always place the red test lead in the 1000 volt jack. Then move it to the lower voltage jacks until the pointer shows a reading in the middle of the scale. The value of the entire scale will be equal to the value of the red lead jack. By starting at the 1000 volt jack and moving to the lower voltages, you will not run a risk of burning out the multimeter. Since most aircraft circuits are 28 volts DC, the 50 volt jack is the one you will use most often. After you have adjusted the function selector switch to direct and plugged the red and black test leads into the proper jacks, you must know how to connect the voltmeter into a circuit properly. A voltmeter should be connected into a circuit so that it is in parallel with the load. You will not damage the meter if you connect it in series, but more accurate readings are obtained in a parallel hookup. You've heard the phrase VIP. In electrical troubleshooting, it means voltmeters in parallel. To get the most accurate voltage reading, connect your voltmeter in parallel with the load. Now we will learn how we prepare the multimeter for use as an ohm meter. Again, we start with the function selector switch. It must be turned to the setting marked ohms. For ohm meter work, the range switch must also be adjusted. In aircraft troubleshooting, the setting R times 1 is most often used. The black test lead goes into the same jack used for voltmeter work, the one marked minus DC plus or minus AC. The red lead goes into the jack marked ohms. All that remains to be done now is to use the ohms zero adjustment knob to zero the ohm meter needle. Connect the test leads together and check the scale. Rotate the ohms zero adjustment knob until the needle is at 0. It is necessary to zero the needle every time you use an ohm meter because ohm meter batteries deteriorate with use and age. The most important thing to remember is this. The circuit must be disconnected from its source of power before connecting the ohm meter. You can do this by turning the switch off, or by pulling a circuit breaker. But the best way is to disconnect the battery. The important thing is to be sure the circuit is dead before you connect your ohm meter. If you connect an ohm meter to a live electrical circuit, you will burn out the meter. Ohm meters are used in aircraft electrical troubleshooting to test for continuity. When we say a circuit has continuity, we mean that it is continuous from the source of power through all the parts and back to the source of power. If a circuit breaker is open, a bulb is burned out, if a wire is broken or a ground is disconnected, the circuit does not have continuity. To test for continuity in a given part of a circuit with an ohm meter, we must first disconnect the source of power. Then we isolate the part of the circuit which is being tested. Isolation prevents false ohm meter indications. Next, we connect the test leads to the two isolated ends of the part of the circuit under test. Since the scale shows a reading, we know the circuit is unbroken. It has continuity. If a wire is broken or there is some other break in the circuit, the needle will not move, indicating that the circuit does not have continuity. The multimeter, when properly used, will help solve both simple and extremely complicated electrical troubleshooting problems. The other two items used in troubleshooting, the jumper wire and continuity test light, are simple compared with the multimeter. The jumper wire is merely a fairly long length of insulated wire with an alligator clip at each end. The continuity test light is another device which you can make for yourself. The materials required are flashlight batteries, a bulb, a length of insulated wire, 2 alligator clips, and a roll of insulating tape. First, the batteries are soldered together in series to provide the necessary voltage. Next, a short length of wire is soldered from the free end of one battery to the primary terminal of the bulb. A wire is soldered to the ground terminal on the bulb, and an alligator clip is attached to the other end of the wire. Another wire is soldered to the free end of the last battery, and a clip is attached to its end. To make your continuity test light easier to handle, you can tape the batteries and bulb together into a compact package. The test light's working principle is very simple. When a circuit is complete or continuous between the 2 clips, the bulb will light. Now that we are familiar with electrical troubleshooting equipment, we will turn to the kinds of troubles we may find in aircraft circuits. Basically, there are only 3 common types of electrical troubles. Open circuits, commonly called opens, short circuits, which are called shorts, and low power. What do these terms mean? An open in a circuit is a break in the circuit's continuity. For example, when a switch is not turned on, there is an open in the circuit. When a circuit breaker pops, there is an open in the circuit. These 2 opens are designed to control a circuit and protect it from damage. Accidental, unplanned opens are the ones we're interested in. For example, a burned-out bulb is an open which is usually easy to detect, but a defective socket or broken wire may be more difficult to locate. Switches can also be the source of an accidental open. Through use or abuse, a switch may fail to close the circuit when it is operated. Loose connections or dirty, corroded connections can also be the source of an open. The mechanical connections on batteries and terminals may vibrate loose or become so corroded or dirty that they fail to complete the circuit. A broken wire anywhere in a circuit is also an open, though this is less frequent than loose terminals or defective units in the circuit. To sum it up, an open is a break in a circuit's continuity. It can be anywhere in the circuit, either in one of the units or in the wiring. We are said to have a short when current flows in paths other than those intended. Actually, there are 3 common types of shorts: shorts to ground, cross shorts, and sticking contacts. Shorts to ground cause a circuit to fail by grounding the circuit before the using unit. Current follows this short path, and part of the circuit becomes inoperative. When a short to the ground occurs, the circuit breaker or fuse will normally open to protect the circuit. This results in a stopping of all current flow. Shorts to ground can occur in any of the units of a circuit or in the wire connecting the units. The second category of shorts is cross shorts. More than one circuit is always involved in a cross short. Normally, when 2 circuits are close together, they are well insulated from each other. But chapping, wear, or abuse may cause the insulation to break down so that the wires touch. Now, when a switch in either circuit is closed, both bulbs will light. Current from one circuit is flowing through both bulbs. Cross shorts can cause many seemingly strange effects. When a light switch is closed, the windshield wipers may operate. Or a landing gear horn may blow. Cross shorts can present tricky troubleshooting problems. Sticking contacts can also cause a short because they cause part of a circuit to be bypassed. A good example is a relay-controlled motor circuit. When the switch is closed, the relay closes and current flows to the motor. Normally, when the switch is opened, the relay will open and shut off the motor. When relay contacts stick, they stay closed even though the switch is opened. Current continues to flow to the motor or other unit. This is called a short because part of the normal circuit is bypassed. This could be caused by a defective relay or by a short in the control circuit. Sticking contacts must be dealt with quickly by disconnecting the power supply at any convenient point, by pulling a circuit breaker or disconnecting a wire. Allowing some relay-controlled units to run too long may damage them severely. Remember, the definition of a short is current flow in an unintended path. Our third common type of electrical trouble, low power, differs from the other two. Low power causes motors to run slowly and relays to chatter and not close firmly. Lights may be dim. The trouble will be in the power supply. The important thing to remember is that the battery may put out 24 volts when it is tested under no-load conditions. The trouble, low battery charge, only shows up when it is tested while connected to power-consuming units. You will find that output may be only 4 or 5 volts when under a load. The solution is to charge or replace the battery. Opens and shorts are our main concern in troubleshooting. How do we know when we have an open and when we have a short? It's not difficult. For example, let's say that this bulb is a navigation light. All that we are normally able to see is the light, the switch, and the circuit breaker. When we close the switch, nothing happens. The bulb does not light, and the circuit breaker does not pop out. Is it an open or a short? If you said open, you're right. A short will always make a circuit breaker pop or blow a fuse. There are rare cases when trouble occurs before the circuit breaker, but this will always cause many electrical units to be non-operative. The bulb did not light, and the circuit breaker remained in. We know we have an open. How do we locate the open? First, of course, we check the navigation light bulb. Odds are it is burned out, but we find the bulb is all right. The socket is clean and the bulb is well seated. We know that we have a circuit open somewhere between the bus bar and the ground of the light bulb socket. First, we go to the aircraft's dash 20 and obtain the wiring diagram, which includes the light circuit we're working on. Like a road map, the diagram will help us to follow the circuit we're interested in from beginning to end. If the wiring diagram has many other circuits on it, it will pay to make a rough copy of our particular circuit. By drawing it, you will learn how the circuit is put together. We have available for testing a multimeter, a continuity test light, and a jumper wire. Most of the testing is done with the navigation light switch on, and testing should be started at the bulb socket and its ground. Such lights are exposed to the weather, and sockets and their grounds can deteriorate. The socket seems firmly attached. Its ground should be good. The jumper wire will tell us if it really is good. If the socket ground is defective, the light should come on when grounded with the jumper wire. It doesn't. The ground on the socket is okay. Now to see whether voltage is reaching the socket. The multimeter used as a voltmeter is the best way to check for the presence of voltage. The red test lead is connected to the primary side of the socket. The black lead is connected to a good ground on the aircraft. The voltmeter shows no voltage reaching the socket. This means that the open must be between the primary side of the socket and the bus bar from which the circuit receives its power. The easiest way to find the open is to start at the bus bar and check for voltage at each terminal along the entire circuit. When we don't get a voltage reading, we know we've passed the open. We can start at the primary side of the circuit breaker since this is the first terminal beyond the bus bar. Here's how it's done. The circuit breaker wiring is exposed and the primary side of the navigation light circuit breaker is located. The red test lead is connected to it. The other lead is firmly attached to a good ground. The meter reads 24 volts, so voltage is reaching the circuit breaker. We continue systematically with voltage checks and find that voltage is present up to the load side of the switch. This means that the open must be in one of the two segments of wire between the switch and the socket. A test at this terminal will determine which of the two segments of the wire is open. With the switch closed, a voltage check is made at the end of the first segment of wire. The scale shows no voltage. This proves that this first section of wire is open and our trouble has been found. If our trouble had been a short rather than an open, the circuit breaker would have opened. The short will keep the circuit breaker open so that the circuit is dead. Here's how we'd proceed to find the short. First, of course, we'd disconnect the battery, then disconnect the circuit's ground. With the circuit breaker open, the circuit is now disconnected from the ground except for the short or accidental ground we're trying to locate. We'd start with a test light or an ohm meter at the load side of the circuit breaker and then at the primary side of the switch. With the switch open, tester current cannot reach the short and complete the circuit through ground. We get no sign of a completed circuit here. This proves the wiring between the circuit breaker and the switch to be good. Next, we'd close the switch and remove the wire from its load terminal. This would isolate the switch and prove whether or not it had an accidental ground. A test of the switch shows that it isn't grounded. The switch is all right. We move on to the next wire junction and disconnect the two segments. When we test here, we will get results. The tester's light will glow or the ohm meter will show a reading. We know this wire is accidentally grounded since there's a complete circuit from it through ground. Two things have helped us to locate this electrical fault. First, careful reference to a wiring diagram. There's nothing which will help more in troubleshooting than a thorough study of a circuit's design before you go to work. And you must know your testers. Know when to use them, where to use them, and how to use them. The multimeter, though it seems complex, only requires a little experience to make you an expert. This mechanic has taken quite a bit of time studying his wiring diagram, but in electrical troubleshooting, a half hour of study on circuit diagrams can save hours of work on the job.